Okay, so I can share screen. Okay, boleh nampak screen saya? Boleh dengar suara jelas?
Nampak doktor, dengar.
Dengar doktor.
Okay, okay, thank you for the response. Okay, so so last week we have stopped until chapter 1 about the introduction to communication system. Okay, so now we're gonna move to chapter 2, which is about the electrical noise. Okay, so this topic also is one of the assignment given to you. Okay, which is the first task about noise. Okay, task assignment itu telah diberikan sebelum ini, and hopefully that the students have start doing discussions, okay, with your group members to discuss, to find the relevant materials, informations, so that you can answer the assignment. Okay, because in the first task you are given 2 questions. Okay, the first one is about the given system with a given parameters. You need to decide which are the best selections based on the given parameters. And for the second questions, you need to think, to suggest what are the other things that can be done to the given system so that we can achieve the best output SNR. Okay, so itu dalam PBL assignment yang pertama. Okay, and hopefully the lecture session today you will learn more about noise. You can have more understanding about the noise topic. Okay, so chapter 2, so we will cover a few subtopics. Okay, the first one is type of noise, and then noise spectral density. Okay, and then signal to noise ratio. So this is so noise spectral density is we known as N0 and not signal to noise ratio SNR. So SNR is the signal power level over noise power level. It is the ratio of signal power level over noise power level. So ideally, we want to achieve SNR as high as possible. Okay, lagi tinggi nilai SNR, lagi bagus. Okay, and then you will learn about noise factor and noise figure. So noise factor, the parameter is F. Noise figure is an F. Okay, noise figure in decibel. Okay, noise factor, there's no unit. Okay, there's no unit, it's a unitless parameter. Okay, so later you're going to learn that F is equal to SNR input, SNRI over SNRO. Okay, signal to noise, input signal to noise ratio over output SNR. Okay, and then freeze formula is used to find F total and also to find NF total. Okay, so tadi NF noise figure is actually equal to 10 log of noise factor. Okay, so freeze formula is used when we have cascaded system. Okay, when we have cascaded system, we want to find the total F and also the total noise figure. Okay, so we use a noise, we use a freeze formula. Okay, and then equivalent noise temperature, which is TE, you will learn later, and you will learn the relationship between TE and F. Okay, noise factor. So there's a relationship between these two. Okay, they're related to each other. And then noise measurement, you will learn about about the average noise, average noise voltage. Okay, at the end of the chapter. Okay, so this is the family tree of noise. Okay, ini dia punya keluarga besar dia. So noise, you see that noise we categorize into two group, which is the first one correlated noise and also uncorrelated noise. Okay, and if you look inside the correlated noise, okay, we can divide into a few parameters, which is for non-linear distortions. We have harmonic distortions and also intermodulation distortion. Okay, so this is under the category of correlated noise. Okay, and then for the uncorrelated noise, we can divide into two groups: external noise and also internal noise. So external noise is the noise generated outside from the system. Okay, so it can be categorized into five, which is atmospheric noise. Okay, the noise generated from the atmosphere. Extraterrestrial noise, which is from outside of the Earth, okay, in the space. It can be categorized into solar noise due to sun activity, cosmic noise due to the movement of comet, and also uh, the things in the space. So that also create uh, noise. Okay, a small, very small amount of noise. Okay. Man-made noise is also known as the industrial noise due to the human activities, okay, in the industry. Impulse noise is a sudden short time of noise. Interference noise. Interference is a special category of a noise. It is also under the group of noise. Interference. We always talk about interference. Interference. So interference also part of noise, but this is the type of noise which have the same frequency as our signal frequency. Okay, so if I transmit signal at 100 megahertz, you also transmit signal at 100 megahertz. So therefore, they're going to be interference. Okay, you will interfere my signal. So we call it as interference. So what happened in the interference? If interference happen, the receiver will be unable to differentiate the type of signal, signal A and signal B. So the signal will mix up. Okay, you will produce a lot of errors at the output of the receiver. Okay, and then for the internal noise is the noise generated within the system, within the transmitter and within the receiver. Okay, so we have short noise, transient time noise, and also thermal noise. Okay, so in this chapter, we will focus more on the thermal noise. The noise uh, that is proportionally the noise level that is proportional to the temperature. The higher the temperature, the higher would be the noise level. Okay, so this is we will focus more on this topic. Okay, and for your information, the correlated noise is more about internal. This is internally happen in the system. Okay, external we only have these types only. Okay, and for your information, this picture has been come out in the previous semester's test. Okay, pernah ditanya dalam beberapa semester yang lepas. We give the students, okay, we give the students this picture. Okay, and we left blanks of some boxes are left blank. So the students needs uh, to put the answer on the given boxes. Okay, so masa tu before the COVID, long before the COVID, so there's no open book. So it is a very simple questions, but many students can answer. Also, many students are unable to answer the question. Okay, it's actually a free bonus question for the students. Okay. Okay, type of noise. There are two types of noise as we learn here in this picture: correlated noise and uncorrelated noise. So, what are the difference? Okay, so correlated noise implies the relationship between the signal and the noise exists only when the signal is present. So for example, here, if we have the system here, for example, transmitter, for example, okay, and here is the signal. So only if we have the input here, okay, only if we have the input to the system, then the correlated noise will exist. Otherwise, there's no correlated noise. Okay, and then if you look from the uncorrelated type of uncorrelated noise, it is a noise that present at all time, regardless of whether you have an input or you don't have the input. Okay, so okay, so if I erase this one, so regardless if you have input or not, uncorrelated noise will exist at all time. Okay, dia tidak bergantung kepada sama ada input atau tidak. Okay, and we can categorize uncorrelated noise into two categories: internal noise and also external noise. So remember, internal noise is the noise generated within the system, within the transmitter or receiver, and external noise is the noise that generated from outside of the system, outside of the transmitter and receiver. Okay, so we look into the uncorrelated noise first. So uncorrelated noise, we can further divide into two categories, which is external noise and also internal noise. So now we want to look into external noise, the noise generated from outside of the system, outside of the transmitter and receiver. Okay, so you see that generated outside of the circuits, there are three primary sources, which is atmospheric, extraterrestrial, and man-made noise. So atmospheric noise is a naturally occurring electrical disturbance originate within the Earth atmosphere. It is also known as the static electricity. Okay, so most static electricity is naturally occurring electrical conditions such as lighting, okay, in the form of impulse, spread energy through wide range of frequency. So this atmospheric noise is insignificant at frequency above 30 megahertz. So above the 30 megahertz, this noise is is irrelevant. Okay, it is not significant. Okay, dia menjadi sangat kecil. Apabila signal itu sangat besar, maka ini menjadi insignificant, maksudnya dia sangat kecil dan pada satu ketika boleh diabaikan. Okay, so dia berlaku pada kita punya atmosfera. Okay, disebabkan oleh electrical static pada atmosphere. Extraterrestrial noise, okay, this is the noise originate from outside of the Earth, okay, which is in the deep space noise. So it is known as a deep space noise. So we can further divide into two of extraterrestrial noise. The first one is the solar noise due to the sun activity. Okay, disebabkan oleh aktiviti matahari. So there are we can categorize two conditions for the solar noise, which is what we call as the quiet conditions, when constant radiation intensity exists and high intensity. And another one is sporadic disturbance conditions caused by the sunspot activity and solar flare-ups, which occur every 11 years. Okay, so matahari dia ada masa-masanya yang mana dia ada, boleh dikatakan ada seperti banyak gunung berapi di dalam itu, yang mana dia akan meletuskan lava-lava apa tu, lava panas tu pada masa-masa tertentu. Okay, so aktiviti matahari tu dia tidak statik, dia seperti gunung berapi sentiasa meletus-letus. So that activities produce these different conditions, quiet conditions and also sporadic disturbance. So sporadic disturbance is a special conditions that happens at certain years. Okay, within 11 years there's going to be flare-ups of fire within the sun. Okay, and then cosmic noise continuously distributed throughout the galaxies. Okay, so ini adalah noise yang extraterrestrial, jenis extraterrestrial noise yang kedua, iaitu cosmic noise, which is happen continuously, okay, throughout the galaxy. So it is a small amount of intensity of noise because the source of galactic noise are located much further away from the sun. So it is often called as the black body noise. Okay, so ini noise ini dia distribute throughout the galaxies. Okay, disebabkan oleh pergerakan objek pada galaksi. So dia mengakibatkan beberapa jenis noise yang sangat-sangat kecil, sangat-sangat kecil. So this is what we call as a extraterrestrial noise. Man-made noise. So this is known as the industrial noise. Okay, it is caused by spark producing mechanism such as commutators in the electric motors, automobile ignition, and etc. So it is impulsive in nature, contains a wide range of frequency that propagate throughout the space, the same manner as radio wave. So dia boleh propagate through the space, seperti radio wave, seperti gelombang radio. Okay, so it is most intense in populated metropolitan and industrial areas. So also known as a industrial noise. So ini disebabkan oleh aktiviti manusia di industri. Okay, so ini memang sukar dielakkan yang ini. Impulse noise is a high amplitude peaks of short duration in the total noise spectrum. Consists of sudden bursts of irregularly sharp consists of sudden bursts of irregularly shaped pulses, more devastating in digital data produced from electromechanical switches, electric motor, and etc. So man-made noise also can be categorized as impulse noise. Okay, remember this is impulse noise. If we look from the perspective of voltage or power, for example, voltage or power versus time, for example. So it happened at a very short time, okay, but at high amplitude. Okay, dia berlaku pada masa yang sangat singkat, tetapi pada amplitude yang tinggi, sudden burst. Okay, so itu dipanggil sebagai impulse noise. Interference, okay, is the noise that has from one source that interfere with another signal. So this is noise type that have the same frequencies with the signal transmitted from the transmitter and from our system. As I explained previously, if I transmit 100 megahertz frequency, you also transmit 100 megahertz frequency. So they're going to be interference. Okay, so your signal will interfere with my signal. So this is what we call as interference. It is a type of noise that has the same frequency as our signal. Okay. And this usually occurs in the radio spectrum. So this is very dangerous types of noise which degrade the quality of our signal. Okay. Internal noise. Okay, so we move to the internal noise, the noise that generated within the system. So there are three primary kinds of internal noise. The first one is the short noise, which caused by the random arrival of carriers. What are the carriers? Carriers are hole and electron. And the output element of the electronic device, such as diode, field effect transistor, or bipolar transistor. Okay, so the current carriers, AC or DC, are not moving in a continuous steady flow, as the distance they travel varies because of their random path of motions. So short noise randomly varying and is superimposed into any signal present. So it is also called as a transistor noise. Okay, so ini dipanggil noise ini disebabkan oleh pergerakan carriers, iaitu hole and electron di dalam device. So ini mengakibatkan noise yang dipanggil sebagai short noise. Transit time noise. Okay, transit time noise. This is related to the movement of carrier. Okay, so it is related to the time of the carrier to propagate through the device. Is an applicable part of the time. One cycle of the signal, the noise become noticeable. So you see that the movement of the carriers throughout the device, so the longer the time taken for the carriers to move from one place to another, so this will cause noise. Okay, the delay of the movement from one place to another for the carriers. So this will cause noise. The higher the delay for the movement, this will cause the higher transit time noise. Okay. So TTN is transistor is determined by the carrier mobility. This is supposed to be in transistor. Is determined by carrier mobility, bias voltage, and transistor construction. Okay. So carriers traveling from emitter to collector suffers from emitter delay. So these kind of delay actually related to the transit time noise. So the higher the delay, the higher would be the transit time noise. Okay. If the transmit delays are excessive at high frequency, the device might add more noise than amplification of the signal. Ini menjadi lebih kritikal pada frekuensi yang lebih tinggi. Apabila kita menghantar signal pada frekuensi yang lebih tinggi, so the higher the delay will give a significant effect to the quality of the signal. Okay, maka ini akan menjadikan noise yang lebih besar. Thermal noise. So this is the thing that we want to focus on, which is the thermal noise. Okay, and I believe this is also related to your assignment, okay, about the thermal noise. So thermal noise due to the rapid and random movement of electrons within a conductor due to thermal agitation. Okay, it present in all electronic components on communication system. Okay, dia wujud dalam semua sistem komunikasi. It is uniformly distributed across the entire electromagnetic frequency spectrum, often referred as white noise. Dia bukan noise color putih, bukan. White, kalau dia menggunakan analogi warna putih yang terdiri daripada gabungan banyak warna menghasilkan color putih. So in this case, dia menggunakan analogi white, putih warna. Dia menggunakan analogi itu untuk menggambarkan bahawa thermal noise ini wujud dalam semua frekuensi spektrum. Okay, regardless of what frequency that you used for transmission, thermal noise still will happen in the system. Okay, so dia tidak bergantung kepada frekuensi. Apa sahaja frekuensi yang digunakan, dia boleh wujud. Okay, it's a form of additive noise, meaning that it cannot be eliminated, and it can increase in intensity with the number of devices and circuit length. Lagi banyak device yang kita gunakan dalam kita punya circuit system, lagi banyak dia punya thermal noise, dia akan accumulate. Okay, so it set up as a upper bound on the performance of the communication system, so temperature dependent, random and continuous occurs at all frequencies. So ini thermal noise, dia berkadar terus dengan perubahan temperature. Lagi tinggi temperature, lagi tinggi thermal noise. Okay. Noise spectral density N0 ataupun N0 is a noise power per unit of bandwidth. Okay, noise power dibahagikan dengan bandwidth. Okay, so that means Pn divide with the bandwidth. So this is in terms of watt divide with hertz. Okay, watt per hertz, which is equivalent to watt seconds or joules. Okay, watt second ataupun watt joules. So if the noise is wide, spread across the entire spectrum, constant with the frequency, then the total noise power N in a bandwidth B is equal to Bn0. Okay, so of course noise power tadi Pn bahagikan dengan bandwidth. So if we want to know Pn, so that means Pn is equal to this Pn over bandwidth multiplied with the bandwidth. Okay, so that's why you're gonna get this Pn. Okay, so this is utilized in the signal to noise ratio calculation. So ini juga parameter yang digunakan dalam SNR calculations. The thermal noise density N0 is equal to K multiplied with T. K is a Boltzmann constant in joules per Kelvin. Okay, K is a Boltzmann constant, joules per Kelvin, and T is the noise temperature in Kelvin. Okay, T dalam sebutan Kelvin. So remember, semua pengiraan temperature untuk noise berkaitan adalah dibuat dalam sebutan Kelvin, bukan dalam sebutan Celsius. Okay, be careful about that. Okay. So N0 is commonly used in the link budget as the denominator of the important figure of merit ratios, EB over N0. EB is a bit energy, okay, bit energy, and N0 is a noise spectral density. Okay, ES is the symbol energy per noise spectral density N0. So what is this actually? Okay, so this we can say that this is a parameter which is similar, okay, not same, similar as SNR in the analog. Okay, in the analog, we use SNR to measure the quality of the signal. We use the SNR parameter, which is signal power over noise power. But in the digital system, we are not using the parameter of SNR. Instead, we are using EB over N0 and also ES over N0, which is this is more accurate for the calculations to measure the quality of the signal. Okay, so dalam digital system, kita lebih prefer menggunakan yang ini berbanding dengan SNR. Okay, so boleh dikatakan bahawa parameter ini adalah setara, bukan sama, setara dengan SNR. SNR kita gunakan dalam analog system, banyak digunakan dalam analog system. Okay. Noise power. So noise power PN, okay, equal to so it is integral of from minus B to B. So this is from the lower frequency to the upper frequency in the bandwidth. Okay, this one. And integral of N0 over 2 DF, okay, over frequency. So equal to N0B. So it can be written as Pn equal to KTB. So enough for you to memorize this equation. Okay, sila hafal equation ini, sila fahamkan equation ini. So Pn is the noise power. The unit is in term of watt. Okay, K is a Boltzmann constant, which is 1.38 times 10 power of minus 3 joule per Kelvin. Bandwidth, the unit is in term of hertz. Okay, T is absolute temperature in Kelvin. Okay, so the room temperature used in your syllabus is 17 degrees Celsius, which is equivalent to 290 Kelvin. Macam mana nak tukar ni from Celsius to Kelvin? Okay, from Celsius to Kelvin. Okay, so you need to plus with 273. Okay, X plus 273. Contoh tadi 17 degree Celsius plus 273. So you will get 290 Kelvin. Okay, so this is the important equations. Okay, so ini many students forgot about this simple formula. Okay, even during the final exam, they forgot about this. Okay, remember to change from Celsius to Kelvin, you need to plus with 273. Okay, so it is clear that the power spectral density of thermal noise increase with the increase of ambient temperature. So ambient temperature means room temperature. Okay, suhu persekitaran. Okay, dalam syllabus kita menggunakan 17 degree Celsius for the room temperature, suhu bilik. Biasa sebelum ni kita guna suhu bilik 25 degree Celsius. So but in this syllabus, in this subject, we use 17 degree of room temperature or ambient temperature. Kenapa macam tu? Sebab ini berdasarkan buku Wayne Tomasi. Okay, dalam Wayne Tomasi dia buat dia setkan room temperature as 17 degree. Mungkin dekat negara dia sejuk, negara kita agak panas sedikit. Okay. So therefore, keeping the electric circuit cool makes their noise level low. So kalau dilihat dalam equation ini, okay, lagi rendah nilai suhu, okay, lagi rendah suhu maka lagi rendah nilai noise power. Okay, lagi bagus. Okay. So kalau kita kurangkan suhu, kita akan menghasilkan noise power yang lebih rendah, which is very good. Okay. And then noise voltage. So we want to relate the noise power with the noise voltage. Kita nak kaitkan perkaitan antara noise power dan juga noise voltage. Okay. So dia menggunakan noise source equivalent circuit seperti ini. So we have the noise source which is connected to the load here, R load, RL. And here Ri is the internal load. Okay. So internal resistance Ri in series with the RMS noise voltage Vn. So Vn here is the voice of the noise source. This is a noise source which is Vn. Okay, sumber noise iaitu Vn. For the worst conditions, the load resistance R here. R load is equal to the internal resistance. So dikatakan di sini pada ketika worst conditions, okay, keadaan paling buruk iaitu apabila load resistance bersamaan dengan internal resistance. Okay, so what happened if the load resistance equal to internal resistance? What happened is that so the voltage drop at the load becomes half of the noise voltage. Okay, so voltage drop pada bahagian load menjadi separuh daripada noise voltage of the source. Okay, so that's why pada di sini voltage di sini VR becomes equal to Vn over 2. Okay, this is during the worst case scenario. Okay, so the noise power Pn across the load resistance is equal to KTB. So now when we want to relate with the power, we use the worst case conditions for these calculations. Okay, kita menggunakan worst case scenario yang mana apabila kita kaitkan dengan noise power, what happen is that you see here Pn is equal to KTB. Okay, so since we are using the RMS voltage, we are using the RMS voltage for the Vn. So therefore, you see that persamaan untuk power, remember that it is Vrms square divide with 2. Sorry, divide with R. Okay, Vrms square divide with R. So now the issue now is during the worst conditions, the voltage drop at the load becomes Vrms over 2. Okay, voltage of the noise divide with 2. So this is at the load side, pada bahagian VR, pada bahagian resistant di sini. So the voltage drop is half of the noise voltage source. Okay, so apabila kita kuasakan dia kuasa 2, okay, dia akan jadi Vn square over 4R. Ini Vn square over 4R yang ini. So Vn square over 4R is equal to KTB. Okay, so therefore Vn square is equal to 4R KTB. Vn square root of 4R KTB. So this is the noise voltage. 4R square root of 4R KTB. So kita menggunakan persamaan ini to find the noise voltage at the load side. Okay. Example. Example 2.2, calculate the thermal noise power available from any resistor at room temperature 290 Kelvin for a bandwidth of 1 megahertz. Calculate also the corresponding noise voltage given R 50 ohm. So here you are given two questions. The first one asks about the thermal noise power. The second part asks about the noise voltage. So for the first part, and the thermal noise power is equal to KTB. So jangan confuse kita boleh guna PN, kita boleh juga menggunakan simbol N. No problem, okay? So previously dia gunakan PN, suddenly he guna N. So it doesn't matter. You can use PN, you can use N, okay? Which is reflect the noise power. So noise power equal to KTB. So K, Boltzmann constant, T is the room temperature, B is the bandwidth, given the bandwidth is 1 mega. 1 mega, 1 times 10 power of 6. So therefore we get 4 times 10 power of minus 15 watt. Be careful about the unit. If you didn't write the unit, that means your answer is wrong. Pastikan jawapan akhir kamu ada unit yang betul. Okay, be careful about that. Okay, I would suggest to students, okay, to highlight the final answer. Okay, biasanya saya suggest kepada pelajar sila gariskan, okay, ataupun highlight macam mana cara pun jawapan akhir. Sama ada you nak buat garis 2 atau you nak buat hashtag, it's up to you. So you need to guide me, you need to guide the lecturer to understand this is the final answer. Okay, why? Because in the final exam, keadaan akan jadi agak huru-hara yang mana jawapan mungkin di atas dia dah kira jawapan dia dekat atas. Maybe jawapan dia dekat sini. So somewhere, anywhere in the paper. Okay, so therefore better to highlight the final answer. Very simple. Okay, so back to the question. Question B asks about the corresponding noise voltage. So we have calculated the noise power. Now we want to calculate the noise voltage. So noise voltage is equal to square root of 4R KTB. So 4 square root of 4 times R resistance. Okay, so this resistance is actually the load resistance at the load side. Yang ini pada bahagian load di sini. So RL 50, so our load is 50 ohm times KTB. KTB we already get the value, which is the noise power over here. So therefore we get 0.895 microvolt. Okay, be careful with the unit. Okay, very easy, very straightforward example. Example 2.3. Okay, kalau ada soalan terus tanya. Kalau ada soalan terus tanya. If you don't have question, I will move to the next slide. Okay, so you are most welcome to ask me questions. Okay, saya mengalu-alukan soalan pelajar. Jangan malu, jangan segan. You boleh, you can always interrupt my lecture. Ask me question. Okay, if no question, I will proceed. Okay, so dalam kelas santai relax. Okay, jangan stress Tak faham boleh tanya. Okay, example 2.3. For an electronic device operating at temperature of 17 degree with a bandwidth of 10 kilohertz. Determine, the first one is thermal noise power, PN, in watt and also dBm. And then determine the RMS noise voltage for a 100 ohm of internal resistance and 100 ohm of load resistance. Ini dia. So kalau dilihat di sini, so dia mencapai worst case conditions yang mana R pada load equal to the R internal. Okay, so if this happen, then we can use this equation for the worst condition. Okay, so therefore the first answer, N equal to noise power equal to KTB, so KTB, and then we get the value 4.002 times 10 power of minus 17 watt. Remember the unit is watt. Okay, so we answer the first part, and then the second part is we need to find in terms of dBm. So noise power in dBm equal to 10 log power divided with the reference value, reference value 1 milli. Okay, so we get the answer negative 134 dBm. So this reference value helps to convert into power to the dBm. Okay, and then what? The second question. So the second question say that Vn is equal to square root of 4R KTB. So 4R, so which R that we want to use? So R here is actually referring to the load resistance. Okay, if you look back here, so this R, okay, this R is actually the load resistance, not the internal resistance. Okay, dia merujuk kepada load resistance. Okay, so therefore we take 100 ohm multiplied with noise power. We already get this one from here. Okay, so ini dia bundarkan kepada 4. So in the exam, in the test, I would suggest you to write up to 3 decimal point. Okay, up to 3 decimal point. Tapi kalau dah macam ni, tak apalah, kalau you nak bundarkan kepada 4 pun tak ada masalah. No problem. Okay, but the final answer, you see that the final answer is you see the up to 3 decimal point, which is highly suggested to the students to write up to 3 decimal point. Okay, so 0.127 microvolt. Okay, ini tak perlu tulis pun tak apa, kerana kita faham bahawa Vn sememangnya dalam RMS. Okay, so this actually, if you look here, this is actually dalam RMS. So we understand that this is RMS voltage. Okay, so if no question about this, I will move.
Doktor,
Ya, silakan.
macam mana tadi nak tahu kalau kena guna worst case tu? Worst condition tu.
Macam mana nak guna nak tahu? Dalam kes ini, in this case memang dia berikan sama. Okay, maknanya R internal sama dengan R pada load. So memang dia nak tunjuk di sini bahawa keadaan ini memang adalah worst case seperti yang dinyatakan di sinilah. Okay, based on this. Okay, for the worst conditions, the load resistance equal to the internal resistance. So therefore we can therefore the voltage drop pada bahagian load adalah separuh daripada noise from the source. Okay, noise voltage from the source. Okay, so the source Vn divide with 2. Ini pada voltage drop pada load pada load, bahagian load. Okay, so therefore dia punya Vn adalah seperti ini. So kita bila kita dalam soalan biasanya memang kita hanya berikan satu jenis resistance sahaja, iaitu load resistance. Okay, yang mana pelajar terus saja menggunakan resistance tersebut. Okay, so dalam question ini dia memang nak menunjukkan dia memang secara jelas nak menunjukkan bahawa ini adalah worst case scenario, yang mana kita boleh menggunakan equation yang ini Vn yang ini for R KTB. Okay, so biasa dalam soalan test soalan exam, we only give a one value of resistance. Easy for you to just put inside the equations for RKTB. Boleh?
Okey, dah faham.
Okay. Example 2.4. Two resistor of 20 kilo ohm and 50 kilo ohm are at room temperature 290 Kelvin. So you are given a two resistor, 20K and 50K, for a bandwidth of 100 kilo ohm. Calculate the thermal noise voltage generated by. So ada dua jenis resistor. Calculate the noise voltage Vn. Okay. So for each resistor, we can create. We're gonna have this one is R1. This is R2. Okay, so we can have 4 R1 KTB and also 4 R2 KTB. Kita boleh kira setiap satu for each resistor. So ini ada solution yang pertama. Kita lihat di sini. Okay, for the first solution, you are given a 20 and 50. So 20 and 50. So we can use a Vn1 as the first noise voltage, which is equal to square root of 4 R1. 4 times R1, 20K, 20 kilo ohm, times times K, Boltzmann constant, times the room temperature, times the bandwidth, which is 100 kilo. Kalau dilihat di sini adalah bandwidthnya adalah 100 kilohertz. Okay, so we get here 5.66 times 10 power of minus 6 volt. Okay, and then for the Vn2, 4 times R2, which is 50 kilo ohm, multiplied with the Boltzmann constant, multiplied with the room temperature, multiplied with the given bandwidth, 100 kilohertz. So the answer going to be 8.95 multiplied with 10 power of minus 6 volt. So ini kalau kita kira secara individual of resistor. Okay. And then question number 2. So what happen if we connect the resistor in series? Okay, so we have here R1, we have R2. Okay. So in this case, we need to find the R total. Okay, dalam kes ini kita perlu cari R total. Kita perlu cari R total supaya kita boleh kira berapakah dia punya total resistance. So total resistance for series connections yang ini 20 kilo ohm plus 50 kilo ohm. So the total resistance for series connection is 70 kilo ohm. Then from here we can calculate the total noise voltage. Okay, so the equation becomes Vn total equal to square root of R total. R total connected in ini saya bahagikan dulu lah. Okay, R total for the series connections multiplied with KTB. Okay, so you see that here square root of 4 times total resistance multiplied with the Boltzmann constant, room temperature, bandwidth. So we get 1.06 multiplied with 10 power of minus 5 volt. Ini cuba guna calculator. Siapa ada calculator, sila cuba buat sekarang. Okay, this is the time for you to practice pushing the buttons of the calculator. Otherwise nanti dalam exam you akan rasa kekok. So you kena cuba sekarang. Betul tak jawapan ni? Kalau jawapan di sini berlainan, you boleh tanya saya. Ada kemungkinan nota ni yang tersilap tulis. So setakat ini belum ada lagi lah. So mungkin kalau kamu tak dapat kira, jawapan kamu berlainan, boleh maklumkan saya. Saya akan cuba explain lebih lanjut lah. Okay. So this is the third question. The third question asks, what if the two resistor is connected in parallel? Okay, so kita ada dua resistor yang disambung secara selari. Okay, dua resistor yang disambung secara selari. So we have R1 and also R2. So how to calculate this? So you need to find the total resistance in parallel. Okay, R total is equal to 1 over R1 plus 1 over R2. Okay, minus 1. So you akan dapat R in parallel, you're gonna get 14.28 kilo ohm. Okay, R disambung secara selari. I assume that you already know how to calculate this. Okay, for the parallel resistance. How to calculate the total resistance for the parallel connections. Okay, so therefore R total is equal to Vn total equal to square root of okay. So biasa macam tu bila ada kelas makin ramai yang cari saya. Okay, tak apa, saya silent dulu. Okay, sambung. So Vn total is equal to 4R square root of 4R total multiplied with KTB. R total here is R total for the parallel connections. So 4 times R total in parallel. So we're gonna get multiplied with Boltzmann constant multiplied with hello. Okay, so sorry about that. So here is square root of 4 times R total in parallel multiplied with Boltzmann constant multiplied with the room temperature multiplied with the bandwidth. So we get 4.78 microvolt. So be careful about this. This is the unit. Okay, so nampak dia punya perbezaan if we calculate one by one and then we calculate the noise voltage for the series connections and also noise voltage for the parallel connections. Okay, so if there's no question to ask, I will move to the next slide. Okay, correlated noise. So ni tadi yang correlated noise, the second type of noise, which is the noise type that always happen regardless whether we have, yeah.
Sorry.
Yeah.
Yang tadi kan, kalau parallel bukan atas dia darab bawah dia tambah.
Yang mana?
Yang 20 tambah 50 tu kan patutnya dekat bawah. Yang darab ke atas kan? R1 R2 over R1 plus R2 kan?
Yang ni So ni kalau you
yang
kira dapat berapa?
Sepatutnya macam terbalik kalau tak silap saya lah formula dia kan.
Sepatutnya dia reverse ni
Dia R1 R2 bagi R1 plus R2.
Okay. So sepatutnya terbalik lah. Secara patutnya dia ada inverse yang ni Macam tu kan maksudnya?
Ya.
So dapat jawapan yang ni ke?
Sekejap.
Kalau saya pakai yang ni senang.
Jawapan dia betul. Tapi yang tu dia tak inverse rasanya.
Sepatutnya dia inverse kan? Betul tak? Okay. Okay, so ini sepatutnya ada inverse lah supaya lebih betul. Okay. So terima kasih kerana betulkan yang ini. So memang ni sepatutnya ada inverse sepatutnya. So saya pun agak pelik juga. Okay. But the answer is correct. But only this pengiraan ini jalan kerja dia. Okay. Okay, correlated noise is a type of noise that that only happen if there is a signal into the system. Okay, correlated noise ini uh, berlaku sekiranya ada signal input kepada sistem. If there's no input signal, there's no correlated noise. Okay, so it is produced by non-linear amplifications and include non-linear distortions such as harmonic and intermodulation distortion. So we can further divide the correlated noise into two types: harmonic distortion (HD) and also the intermodulation distortion. So what are the difference? So harmonic distortions is the unwanted harmonics of a signal produced through nonlinear amplifications, which is nonlinear mixing. Harmonics are integer multiplies of the original signal. Okay, so kalau you ada signal, kalau kita lihat dalam dalam frequency domain. Okay, so for example, this is a voltage versus frequency. So if this is your signal, you're gonna have harmonics. Okay, so the non-linear mixing produce these small harmonics. Okay, katalah ini adalah original signal. Okay, because of this mixing, it produce additional spectrum, frequency spectrum, yang mana dia punya amplitude lebih kecil. Dia akan berserakan. Saya gunakan perkataan berserakan dalam spektrum itu. Okay, bersebelahan dia dalam spektrum bersebelahan. Okay, disebabkan oleh non-linear mixing ini, maka wujudnya harmonik. Okay, harmonik iaitu frekuensi spektrum yang mempunyai amplitude yang kecil pada frekuensi yang berbeza. So this harmonic can be eliminated by using the filter. Kita boleh buang dia menggunakan filter ataupun ada kaedah yang lain. Okay, so there are various degrees of harmonics. Second order HD, so ni sepatutnya HD. HD for harmonic distortion. So second order is the ratio of RMS amplitude of the second harmonic to the RMS of the fundamental. Okay, so nanti ada contoh, nanti kita akan lihat. Okay, nanti kejap. Okay, third order is the ratio of RMS amplitude of the third harmonic to the RMS of the fundamental. Apa itu fundamental? Fundamental adalah yang ini original frequency spectrum yang asal daripada kita punya signal. Okay, signal kita itu adalah fundamental frequency. Harmonic wujud second order, third order, fourth orders, fifth order, sixth order dan seterusnya. Okay, nanti kita akan lihat. Total harmonic distortion THD is the ratio of quadratic summation of the RMS values of all the higher harmonics from second order to n order. Okay, to n order of harmonics. Nanti kita akan lihat. Divide with the divide with the fundamental. So apa benda ni kita akan lihat di sini. So lihat gambar raja ini yang atas, gambar raja A. Okay, gambar raja A. So if we look from the definition of harmonic distortion, it is the unwanted harmonics of a signal produced through nonlinear amplification or nonlinear mixing. Harmonics are integer multiplies of the original signal. Maksudnya di sini kita ada satu input frequency. The keyword here is of a signal. A signal with a single frequency. Okay, kita ada satu input. So what happened? Kalau dilihat di sini yang bahagian sini so we have the input here at F1 the amplitude here is V1. So this is the original, which is the input. And after the non-linear mixing, okay, after the non-linear mixing in the device, maka wujudnya harmonics. Iaitu yang ini second order harmonics, third order, fourth order dan seterusnya. Okay, depend dia boleh jadi banyak. Okay. Dan frekuensinya adalah di manakah lokasi harmonik? Lokasi harmonik adalah kita darabkan sahaja dengan integer. Kalau second order kita darabkan dengan 2, third order darabkan dengan 3, fourth order darabkan dengan 4. So bermakna dia terletak pada 2 kali F1, 3 kali F1, 4 kali F1. Itu dia punya location dalam spektrum, dalam frekuensi domain. Okay. Dari segi kedudukan harmonik, dia terletak pada 2 kali F, 3 kali F, 4 kali F, sehinggalah N kali F. Macam mana dia punya amplitude? Ketinggian dia, dia punya kekuatan dia. Amplitude dia adalah V2, V3, V4, V5 dan seterusnya. Kalau dilihat dia punya the harmonics, the amplitude of the harmonics is smaller compared to the compared to the fundamental frequency or the original frequency F1, which is V1 over here. Okay, so fundamental frequency juga dipanggil sebagai first order harmonic, tetapi dia bukan harmonic di sini ada dibuat sebagai first order, sepatutnya dia dikategorikan sebagai fundamental frequency. Okay, fundamental frequency yang asalnya dia bukan harmonic. Apabila kita ada tambahan, maka itulah dia harmonics. Okay, so how do we calculate the second order? Yeah. So second order is the ratio of, okay, tadi second order HD is equal to tadi apa, V2 divide with V1. Okay, second order. Third order of HD is equal to V2 over V1. Fourth order of harmonic distortion is equal to ini V3 sorry. Okay, yang ini V4 over V1. Okay, and sometimes we also find the value in terms of percentage. Kalau diminta cari dalam sebutan percentage, maka you perlu darab dengan 100%. Okay, V2 per V1, V2 over V1 or multiplied with 100%. Third order V3 over V1 multiplied with 100%. Fourth order V4 over V1 times 100%. Ini untuk mencari yang tadi yang ini. Second order, third order, fourth order, fifth order, sixth order dan seterusnya. Okay. Macam mana pula nak cari total harmonic distortions? Total harmonic distortions, okay. So we need to find, first of all, we need to find the ini disebut di sini V higher over V fundamental. Okay. So V higher, what is V higher? V higher is the quadratic summation of the RMS voltage for the harmonics. Okay. So kita buat quadratic summation for the harmonics. For example here, V2 square plus V3 square until, okay, ni ada dot-dot until Vn square. Sehinggalah Vn square. And then we do the square root. Okay, so we get the V higher. V higher di sini adalah quadratic summations of the harmonics. And then divide with V fundamental. V fundamental here is V1. Okay, V fundamental di sini bermaksud V1. Okay, so quadratic summations of the harmonics divide with V1, which is the fundamental frequency or the original frequency. Then we multiply with 100% because we want to find the value in terms of percentage. Okay, so hasilnya kita akan dapat dalam sebutan persen X percent. Okay, X percent. Nanti ada contoh kan? Nanti ada contoh selepas ini. Nanti kita akan lihat contoh. Okay. Kemudian intermodulation distortion. Okay, ni kalau tak ada isu saya akan teruskan. Intermodulation distortion is the generation of unwanted sum and difference frequency when two or more signals are amplified together in a non-linear device such as signal amplifier. Nah, so ini kalau ada satu sistem, kita ada input, at least perlu ada 2 atau lebih input. Okay. So dengan adanya 2 atau lebih input ke dalam satu sistem, maka proses mixing ini akan menghasilkan unwanted sum and unwanted difference frequency. Remember the keyword here is this one. We have 2 or more, 2 atau lebih input. Yang tadi harmonic distortion cuma ada satu input saja, a signal. Okay. Now for the intermodulation distortion, we need to have at least 2 input into the systems, and through the non-linear mixing, okay, through the non-linear mixing and amplifications in the system, maka akan wujudlah harmonics. Tetapi harmonics ini dipanggil sebagai sum and difference. Apa beza dia? So kita akan lihat gambar di sini. So ini saya padam sikit. Ini theoretical concepts dia, you kena fahamkan juga yang ni. Saya padam dulu, saya buat ni. So now we look at picture B. Okay, this picture. So you see that here in this example, they gave 2 input. Okay, 2 input. We have input F, input pada frequency F1, the voltage is V1. Input at F2, voltage is V2. So these 2 input put inside the system, there's gonna be a non-linear mixing, non-linear amplification inside the system. What happen is that we're gonna produce unwanted sum and difference. So this is also harmonic. Ini juga dipanggil harmonic sebenarnya. So what is unwanted sum and difference? Unwanted sum means that they're gonna be a harmonics that exists at the frequency of F1 plus F2. Okay. Unwanted difference is harmonic that exists at frequency F1 minus F2. So the word sum adalah hasil tambah frekuensi. The word difference adalah hasil tolak frekuensi. Di mana kedudukannya? Okay. So the word sum and difference is referring to the locations of the frequency. Dia merujuk kepada lokasi frekuensi pada spektrum. Okay. So you see that here after the non-linear mixing, so you see that we have a input signal, the fundamentals, we have F1 and F2. And through this non-linear amplification, maka wujudlah 2 lagi, at least ada 2. Dia sebenarnya ada banyak. So untuk pengetahuan semua pelajar, sebenarnya dia ada beberapa harmonik lagi yang kecil-kecil ya. Ada beberapa lagi sebenarnya. But for the theoretical concept, we want to make you understand about these critical conditions, about this. The dominance is at the sum and difference. So dia akan mengganggu kita punya proses modulation nanti sebenarnya. Okay. So for your information, there's some other harmonics, small harmonics, which is not stated here, okay, because we want to focus about these issues, sum and difference. Okay, so pada sum and difference berlakulah satu harmonic yang dominance, iaitu dipanggil sebagai intermodulation distortion. So ini juga melibatkan proses modulation. Apabila kita buat proses modulation, remember modulation is also a process of mixing. Ingat modulation juga adalah proses mixing. So ini juga akan menghasilkan intermodulation distortion, yang mana kita perlu faham bahawa dalam filter design dia perlu eliminate this sum and difference. Be careful. So dia punya konsep itu. So that means we need to design a filter that can eliminate or reduce the effect of intermodulation distortion. Okay. So kita pergi kembali kepada ini. So the sum and difference frequency are called the cross product. Okay, both sum and difference are called the cross product. Okay, kita fokus kepada dua bahagian ni, sum and difference. Walhal ada sebenarnya harmonik-harmonik yang kecil. Okay, so you focus on that too, because this is the critical point. So the sum and difference, what we call as a cross product. Okay, kedua-dua ini dipanggil sebagai cross product. Okay, so figure. Okay, we already look at the figure. So mathematically, cross product, which is the sum and difference frequencies, are calculated as MF1 plus minus NF2. Macam mana nak cari cross product? Ini cara dia. MF1 plus minus NF2. Okay, because we want to find the sum and difference. Cross product ini tujuannya kita nak mencari sum frequency and difference frequency. And that's the purpose of cross product. And remember that F1 must be more than F2. Kalau F1 kurang daripada F2, maka kita akan dapat negatif. Okay, so tidak ada negative frequency. There's no negative frequency. Okay, so M and N are positive integers between 1 and infinity. Nilai M dan N boleh jadi 1 sehingga infinity. Okay, sebarang value. Nanti ada example ni kita akan lihat. Okay, so ini cross product juga pernah ditanya dalam test, yang mana kita ambil daripada example. We take from the example, we give this that one as a test questions. So this is a prior to the long before the COVID pandemic. Okay, so nanti kita akan lihat contohnya. Example 2.5, this is regarding the harmonic distortion. Okay, this is regarding the harmonic distortions. So question number 1, you are given okay, so you need to determine the second, the third and 12 harmonics of a given 1 kilohertz repetitive wave. So this is, we can say that this is the fundamental frequency. Okay, fundamental frequency. Okay, so sekarang soalan yang pertama cuma cari nilai harmonics. Di manakah lokasi harmonik untuk tiga harmonik, second, third and 12. Ada 3. So di mana kedudukannya? So we can see from here, the answer you see from here. Second order harmonic is located at 2 times the fundamental frequency, 2 times 1 kilo. So that means it is located at 2 kilohertz. Okay. Third order harmonics, 3 times the fundamental frequency. So it is located at 3 kilohertz in the spectrum. 12 harmonics is located at 12 times the fundamental, 12 times 1. So 12 times 1 kilo, so we get the location is at 12 kilohertz. Ini baru nak tahu dia punya location sahaja. Okay. And then what? Find the percent of second order, third order and total harmonic distortion for a fundamental frequency with amplitude of 8 volt RMS. Okay, so that means that you are given a V1, V fundamental is equal to 8 volt, and then you are given a second harmonic amplitude V2 is equal to 0.2 volt, and then you are given V3. V3 is equal to 0.1 volt. Okay. So ini soal, this question is we can say that it is not related to the first question. Okay, kita boleh kata dia lain sedikit daripada yang soalan pertama, kerana soalan pertama dia tanya sehingga 12. Okay, so the second question they only give second and third order harmonic. Okay, and then you need to find the THD. Okay, but before we find the THD, we need to find the second order harmonic distortion, second HD, third HD. Okay, so second order harmonic distortions is equal to V2 over V1 multiplied with 100%. Okay, so we get 2.5%. Third order harmonics, V3 over V1 times 100%. So it is 0.1 over 8 multiplied with 100%. Okay, so this is 100%. So we get 1.25%. Okay, and then the question asks, how much is the harmonic distortion up to third order? Jangan confuse dengan 12 order tadi. Tadi dia tanya 12 harmonic. But for this question, dia tanya how much is the total harmonic distortion up to third order, sehingga third order. Okay, so that means total percentage of total harmonic distortion is equal to square root of this is the summation of V2 as summation of V2 square and also V3. Okay, summation, quadratic summations, 0.2 square plus 0.1 square and then square root. So we get the quadratic summations. Okay, square root of quadratic summations, divide with V1, 8 volt, and then multiplied with 100% to get the percent. Okay, in terms of percentage. So total harmonic distortion up to third order, okay, sehingga third order, jumlahnya adalah 2.795%. Okay, so if the question give you up to up to, for example, up to 5th or 6th or whatever n order, so you need to plus again. So if there's more, kalau diberikan lebih, maknanya you kena tambah lagi lah. Maknanya V3 square plus V4 square plus until Vn square, and then divide over V1. Tapi soalan ini sehingga sorry, saya padam dulu lah, confuse nanti je. Tadi sampai V3, sepatutnya V4 lah kat sini. So ni kalau saya panjangkan lagi, so ini, so this is a V3, so V4 square plus V5 square plus until Vn square, sehinggalah Vn square. Okay, and then divide with fundamental frequency voltage V1 multiplied with 100%. Okay, and then kalau tak ada soalan, saya akan teruskan kepada example seterusnya. Okay, example 2.6. So this is about intermodulation distortion, ataupun saya boleh tulis sebagai ID, intermodulation distortion. Okay, sorry. Okay, so this is intermodulation distortion. So for a non-linear amplifier with two input, daripada sini kita dah tahu two input frequencies. So that means this is not harmonic distortion, this is related to intermodulation distortion. We have two input, okay, at 3 kilohertz and at 8 kilohertz. Determine the first three harmonics present in the output of each input frequency. Tadi sebenarnya apabila kita mix up both of these frequency, akan wujud sum and difference. Macam saya sebutkan tadi bahawa sebenarnya wujud harmonics yang kecil. Okay. So kalau kita nak lihat di manakah kedudukan harmonics yang kecil itu, so we can find the location of the harmonics. Ni You see that here for the first input. First input is 8 kilohertz, second input is 3 kilohertz. For the frequency of 3 kilohertz, okay, so ni dia tulis first harmonics. Sepatutnya ini bukan dipanggil harmonics sebenarnya, tapi ikut buku lah. Some books tulis first harmonic, some other literature books they wrote as fundamental. Okay, so this is actually fundamental. Okay, fundamental frequency. Okay, so fundamental 3 kilohertz. Second harmonics, third harmonics. So second harmonics located at 2 times 3, third harmonics located at 3 times 3. So the second harmonic 6 kilohertz, third harmonics 9 kilohertz. These are the harmonics for 3 kilohertz. And then if we look at 8 kilohertz, so the fundamental is 8 kilohertz. Second harmonics and third harmonics located at 2 times 8 and 3 times 8. It is located at 16 and 24 kilohertz. Ini di mana lokasi dalam spektrum. Okay, harmonic untuk setiap input. Okay, apabila kita ada dua atau lebih input put inside the system, okay, through the non-linear amplifications, of course, there going to be intermodulation distortion, akan ada sum and difference, and there's also a small harmonics. These small harmonics, we can estimate the location of the harmonics based on these equations. Okay, for the first input, di mana lokasi dia adalah 2 kali 3, 3 kali 3, 4 kali 3, dan seterusnya. Okay, kita boleh cari banyak-banyak harmonics. Di manakah lokasi harmonics? Sama juga untuk second input, third input, fourth input. So dalam kes ini second input 8K, okay, 8 kilohertz, dia punya location of the harmonics yang kecil-kecil itu, harmonic yang kecil-kecil terletak pada 2 kali 8, 3 kali 8, dan mungkin kalau ada 4 kali 8, 5 kali 8 dan seterusnya. Okay, depending on the harmonics. Okay, so now we know the location of the small harmonics. Okay, ini belum masuk yang sum and difference, belum lagi. Kita baru nak melihat di mana dia punya lokasi harmonik yang kecil-kecil itu. Okay. Okay, so kita dah identify, oh dia punya harmonik yang kecil-kecil itu terdapat pada frekuensi-frekuensi sekian. Okay. Then the second question asks the cross product frequencies given M and N, 1 and 2. So soalan yang kedua, kita nak melihat di manakah lokasi sum and difference. Okay, di manakah lokasi sum and difference? Di manakah lokasi sum and difference jika diberi M dan N sebanyak 1 dan 2? Dalam kes ini bermaksud M bersamaan dengan 1 dan juga 2. N bersamaan dengan 1 dan 2. So dalam kes ini dia berikan 2 value untuk setiap M dan N. Ni jangan confuse. Nanti kita akan tengok contohnya. Maksudnya M ada 1 dan 2, N juga 1, 2. So ada 2 value untuk setiap M and N. M nilai dia 1, 2, N nilai dia 1 dan 2. Okay, so what happened? So jika itu berlaku, maka kita perlu buat, sebaiknya kita buat dalam bentuk table. Okay, kita perlu buat dalam bentuk table, yang mana kalau dilihat dalam table ini, dia senaraikan M, N dan juga cross product. Okay, so M boleh jadi 1 dan 2, N juga boleh jadi 1 dan 2. So maka akan ada 4 kombinasi. 2 kali 2. Akan ada 4 combination. Sekiranya M sama dengan 1, N1, M1, N2, M2, N1, M2, N2. So akan ada 4 combination. Okay, ni minta maaf, ini memang ayat ini dia agak mengelirukan sedikit. Takut nanti kita biasa menganggap, oh M1, N2. Sebenarnya dia di sini dia merujuk kepada ada dua value untuk setiap M dan N. Okey, ayat ini agak mengelirukan juga sebenarnya. So where are the cross products? The location of the cross product. Di manakah lokasi cross product itu? Okay. So for the first scenario, ini saya padam sikit. For the first scenario, M. So remember that the formula is like this: MF1 plus minus N F2. Okay, where F1 is larger than F2. Of course, yang ini 8K, yang ini adalah 3K. Okay, so kalau MN1, so that means 8 plus minus 3 kilohertz. So the cross product will be located at 5 kilohertz and 11 kilohertz. So 5 kilohertz is a difference frequency, 11 kilohertz is the sum frequency. Okay. Kalau dilihat untuk second combination, M1 N equal to 2, that means 8 kilohertz plus minus 6, because this is 3 times 2. Okay, so 8 plus minus 6, therefore the location of the cross product is located at 2 kilohertz for the difference frequency and 14 kilohertz for the sum frequency. Okay, if you look at the third combination, M2 and 1, that means it is equal to 16 kilohertz. So 16 is actually 8 multiplied with 2 plus 3 kilohertz. So the cross product would be 13 kilohertz for the difference frequency and 19 kilohertz for the sum frequency. Okay, tadi 16 tolak 3 dapat 13, 16 tambah 3 jadi 19. Okay. And then for the fourth combination, M equal to 2, N equal to 2. So therefore here is 8 times 2, 16. 3 times 2 becomes 6. So 16 minus 6 becomes 10 kilohertz for the difference. 16 plus 6 becomes 22 kilohertz for the sum frequency. Nampak So dia punya location akan berada pada sekian location berdasarkan nilai pendarabnya M dan juga N. Okay. So this is the location of the cross product. Okay. Boleh Kalau tidak ada pertanyaan, saya akan teruskan kepada slide berikutnya. Okay, so this is ini cross product adalah hasil tambah dan tolak. Remember that cross product adalah hasil tambah dan tolak. We want to identify the location of the difference and also location of the sum frequency. If you look from the picture here, okay, kita nak kenal pasti lokasi ini lokasi difference dan lokasi sum frequency. We want to identify the location, okay, using the cross product equation. Okay, so if there's no questions, I will move to the next slide. Okay, saya akan pergi kepada slide berikutnya. Slide berikutnya akan menjadi lebih menarik. Okay, saya jangka yang seterusnya ini adalah topik-topik yang pendapat saya mungkin lebih menarik pendapat saya sebab dia ada banyak pengiraan dan dia tidak terlalu bebankan dengan theoretical concept. We calculate based on the given parameters. Okay. So signal to noise ratio SNR ini juga dalam you punya assignment. Okay. Signal to noise ratio is the ratio of signal power divide with the noise power. Okay. So the symbol is S over N ataupun boleh juga kita buat sebagai PS over PN. PS over PN is equal, PS is the signal power, your signal. The unit is in term of watt. PN is the noise power, the unit is in term of watt. So when we divide power and power, so these produce a unitless parameter. Dia tidak ada unit. but dia adalah nisbah. Okay, and when we convert this into decibel, dia akan jadi signal to noise ratio in term of decibel becomes 10 log PS over PN. So unitnya adalah dalam sebutan decibel, dB. Okay. So if the input and the output resistance of the amplifier, receiver or network being evaluated are equal, okay, so therefore, okay, you see that the resistance are equal. Ni telah diberikan di sini. So kalau kita nak mengukur dalam sebutan voltage, okay, so what happened is that you see that here 10 log. So it is actually like this. Okay, so power, remember power, kita boleh kira dalam VRMS square over R, ataupun kita boleh mengukur dia dalam sebutan V peak, okay, peak value dibahagikan dengan 2R. Ni saya rasa pelajar pun faham berkenaan perbezaan antara peak value dan juga RMS value. Okay, nanti kita akan lihat. So dalam kes ini kalau dilihat saya ambil contoh, tak kira lah sama ada dia RMS ataupun sama ada dalam sebutan peak value. Okay, so kalau kamu lihat di sini kalau saya katakan saya gunakan peak value for example, okay, so it is actually like this. So Vs square over 2R. Okay, so Vs square over 2R divide with Vn square over 2R. Yang mana di sini dikatakan resistance are equal. Okay, that means we can cross out, kita boleh keluarkan nilai 2R ini, so dia menjadi Vs square over Vn square. Okay, which is kita boleh tulis macam ni lah, Vs over Vn square. Okay, so therefore 10 log Vs over Vn square, it becomes 20 log of Vs over Vn. Okay, so nilai 20 log ini bukan nilai magic, dia berdasarkan perubahan kita punya penukaran daripada power equation to become the voltage equations. Okay, dia jadi 20 log Vs over Vn. Okay, so straightforward. Example, for an amplifier with the output signal power. Okay, before that, we look into the system. Okay, so system dia mesti ada input dan juga dia ada output. Okay, output. So you see that SNR can be in the input and also can be at the output. Okay, kalau kita mengukur SNR pada input, dia boleh jadi bermakna dia adalah SNR I. Dia adalah input signal power divide with the input noise power. Pada bahagian output kita juga akan ada, kita boleh kira juga dia punya SNR. Okay, SNR O. Yang mana dia adalah output signal power divide with the output noise power. Of course di dalam sini akan ada pelbagai macam device yang mana dia akan mengakibatkan perubahan pada input, so dia menghasilkan output S dan juga output N. Okay, nanti kita akan lihat macam mana nak kira SNR input dan juga SNR output. Okay, sama macam dalam you punya assignment. Dalam you punya assignment, you boleh lihat bahagian input dan juga output. Okay, you can measure the input SNR, you can measure the output SNR, and you can measure the noise factor. Okay, so kembali kepada sini go back to here. For an amplifier with an output signal power, okay, you are given output signal power and output noise power. Ni dia cerita pada output system lah. Okay, SO and also NO. So how much is the SNR O? Itu ditanya macam tu So SNRO is equal to signal power over noise power, which is 10 watt divided with 0.01 watt, so you get 1000. Dia tidak ada unit. Ini tak perlu tulis dalam exam pun tak apa. Okay, ini cuma nak memberitahu kepada kita bahawa ini parameter ini tidak ada unit. Okay. Dia tidak salah kalau tulis, cuma agak lucu sedikit lah kalau you tulis unitless. We know that if you don't write anything becomes unitless. Okay. Sebab ada pelajar yang dia tulis unitless. Dia mengikut seperti dalam nota. But remember that if you just write 1000, we understand that it is a 1000 without unit. Okay. So kemudian SNR in decibel, 10 log 1000 becomes 30 dB. Remember to write the unit. If you don't write the unit, your answer will be wrong. Jawapan kamu adalah salah. Okay, ada beza antara 30 dan juga 30 dB. There are difference. Okay, so be careful about that. And then what? And then for the next example. Okay, kalau ada soalan boleh terus tanya. Saya bersedia untuk menjawab soalan. Kalau tak ada, saya proceed. So example 2.8, for an amplifier with the output signal voltage 4 volt and output noise voltage 0.05 volt, and input and output resistance is 50 ohm. So kedua-dua resistance pada input dan output adalah 50 ohm. Determine the signal to noise ratio. Okay. So you are given the signal voltage and also the noise voltage. Okay. So therefore, when you want to write the SNR, that means the Vs square over R divided with Vn square over R. Okay. So I assume this is the RMS value. Sebab dia bahagikan dengan R. So Vs square over R over Vn square over R. So you can cancel out the resistance value. So it becomes 4 square over 0.05 square, which is 640,000. Okay. This is a no unit it is a unitless parameter without a unit. And when we want to convert into decibel, 10 log of 640,000, so dia menjadi 58 decibel. Cuba guna kalkulator, cuba tekan kalkulator. Biasakan menekan nilai button log, anti log dan sebagainya supaya kita terbiasa membuat menggunakan kalkulator. Ini dia. Noise factor and noise figure. So these are the favorite topics in the test and final exam. For sure, this will come out in the test and final exam. Pasti akan keluar. Okay. Sebab inilah dia punya fokusnya adalah di sini sebenarnya. The focus of chapter 2 is towards this subtopic actually. So noise factor is equal to input SNR divide over output SNR. So if you see that this is SNR input, bahagikan dengan SNR output. Be careful bukan output over input. Now this is input over output. And it is a unitless. Okay, because SNR, remember when you do this calculation, you must make sure that both SNR are unitless. Jangan bahagi decibel dengan decibel. Be careful about that. Okay. Make sure that SNR is a unitless parameter. Then you can do the division. Okay. You cannot do in terms of decibel. Tidak boleh buat dalam sebutan decibel. Be careful about that. Because this is the most common mistake by the students. They are given the SNR in terms of decibel, dia terus masukkan dalam persamaan F, which is wrong. Kalau salah di sini, maka yang seterusnya akan salah, habis. So be careful about that. Okay, so remember this is a unitless and unitless. don't put decibel inside this equation. Okay, jangan letak nilai decibel dalam parameter F. Okay. So noise figure, so now we want to calculate the in decibel. Noise factor in decibel is what we call as a noise figure. So 10 log SNRI over SNRO. Okay, SNRI, SNRO. Okay, so 10 log F. Okay, so you see that here we actually theoretically we want the value of F to be as minimum as possible. Okay, secara teoretikalnya kita inginkan nilai noise factor itu sekecil yang mungkin. Sebab dia yang paling kecil adalah 1 untuk noise factor. Okay, so for the ideal case, for the perfect system, okay, perfect here is ideal. Ideal maksudnya tidak ada gangguan, tidak ada noise di dalam situ. So what happen is that F equal to 1. Maksudnya input bersamaan dengan output. Sorry, dia bukan tak ada noise, dia ada noise. Noise is still happen, but the ratio becomes same. It's a perfect system. That means that there's no internally generated noise. Hanya ada amplifier which improve the gain of the signal and also the noise. So pada akhirnya the ratio become the same. Nanti kita akan lihat contoh. Okay. So F paling kecil, the best is equal to 1. Okay, SNR input sama dengan SNR output. This is the ideal case, perfect system, which is not exist in the real world. Dia tidak wujud dalam dunia sebenar. Okay, secara teoretikalnya kita inginkan nilai F sekecil yang mungkin, iaitu menghampiri nilai 1. We want the value of F to be almost near to value of 1, because 1 is a perfect. Okay, kita lagi besar nilai F bermaksud nilai jumlah noise dalam sistem itu semakin banyak. Okay, so if F equal to 1 during the ideal case perfect system, that means noise figure becomes 0. So 10 log 1 equal to 0. Okay, 0 dB. So that means we want the noise figure to be as small as possible towards 0 dB. Okay, kita mengharapkan sistem kita mempunyai noise figure menghampiri 0 dB. Okay, walhal 0 dB ni adalah perfect. Very perfect. Okay, sangat perfect. Okay. So okay. Okay, for this one I want to show based on this. So saya akan skip yang ini. Ini sama, saya akan tunjuk yang inilah sebab dia berdasarkan gambar. Okay, so dia berdasarkan gambar. Okay, so I skip to the picture so that lebih jelas. Ini sama dengan gambar yang ini. So penerangannya dia ada dua bahagian. Kita lihat di sini ada dua bahagian. Okay. So the first about picture A is about the ideal noiseless device. Noiseless device. Bermaksud apa? Bermaksud device ini tidak menghasilkan additional noise. Dia tidak menghasilkan noise tambahan daripada input. Input memang ada noise. Of course we have noise from the input, from the surrounding. Masuk ke dalam sistem. So dalam sistem itu perfect. Dia tidak menghasilkan additional noise. So that's why we call it as an ideal noiseless device. Okay, device itu sendiri dia tidak menghasilkan additional noise. Dalam case ini dia cuma ada amplifier which will produce the gain. Okay, so what happened? So let's look here. So here we have a input SI over NI. Okay, SNRI. So SNRI is SI over NI. And then here the system only have a gain, power gain. Okay, so what happened at the output? Apa yang berlaku pada output adalah output signal power becomes input signal power multiplied with the gain. So APSI. Okay, we multiplied input signal power with the gain. Okay, what happened to the noise? Input noise power multiplied with the gain. Of course, if we have the gain, the amplifier, okay, the amplifier not only amplify the signal, it also amplify the noise. So kalau noise yang masuk itu besar, dia akan jadi lagi besar. Okay, so that's why we need to be in the real world. We need to minimize the input noise so that we can achieve a better output SNR. Okay, so remember that amplifier not only amplify the signal, it also amplify the noise. Okay, so that's why APSI multiplied with APSI divide with APNI. Okay, so output signal and output noise. So if you see from here, the ratio is still the same. Okay, it is SI over NI, which is actually SNR input. So ini dipanggil sebagai perfect system, yang mana dia punya nilai F bersamaan dengan 1, NF bersamaan dengan 0 dB. Okay, this is a perfect system, which is not exist in the real world. This is a theoretical concept. Okay, let's look at the second picture, picture B. Amplifier with internally generated noise. Maknanya, dia sistem itu menghasilkan noise tambahan di dalam sistem itu. Okay, so we look here, we have the input, okay, signal power, we have the input signal power, we have the input noise power. And then in the system, it has a gain, power gain, AP, and it has another parameter, ND, which is internally generated noise. Ini yang baru, internally generated noise. So what happened in the output? Apa yang berlaku pada output? So the output is equal to, okay, output signal power is equal to AP multiplied with SI. Gain multiplied with the input signal power. So we get S out. What about N out? N out is equal to input noise multiplied with the gain plus. Ini berhati-hati, dia plus. Input noise power multiplied with gain plus with internally generated noise, ND. Okay, so SI over NI plus ND over AP. So ni kalau kita rumuskan balik lah, dia jadi macam ni. So ni tak perlu keliru lah, ni tak perlu confuse yang ini. So apa yang kita lihat di sini if we look from here, that means the SNRO is smaller than SNRI disebabkan adanya internally generated noise. Okay, SNRO ini menjadi lebih kecil daripada SNR input. Okay, disebabkan adanya tambahan-tambahan noise tersebut. Okay, ideally kita nak SNR out sama dengan SNR input. That's the ideal case. Tetapi dengan adanya internal noise ini, maka SNRO lebih kecil daripada SNR input. Okay. So dalam case ini, for this case, F will be larger than 1 and F will be larger than 0. Okay, will be larger than 0 dB. Nanti ada contoh-contohnya kita boleh lihat. So this is for the one system, one system only, one device only. What if we have many devices connected in series, cascaded? Okay, we call it as a cascaded. So dalam you punya syllabus, kita melihat kepada contoh amplifier. Okay, we have amplifier connected in series, cascaded. Biasanya kita tanya sehingga 3 saja dah cukup. Cascaded up to 3 amplifiers. And now the issue is how we want to calculate the total F, total noise factor. Macam mana cara nak mengukur a total noise factor? So we need to use the Friis formula. Okay, so let's look from this picture. Kita perlu melihat picture ini untuk fahamkan equation. In order to understand these equations, we need to look from this picture first. Kita perlu fahamkan gambar raja ini. Perhatikan. So we have the input, from the input we have the input signal power, noise, input noise power. Okay, and the signal goes into the system and it will goes into the amplifier 1 and then amplifier 2 and then amplifier 3. Okay, kalau you lihat di sini dia akan berganda, dia punya gain itu akan berganda kerana kita ada 3 amplifier dalam example ini. Okay, now let's look from here. So the first amplifier has a gain of AP1 and then the third amplifier is has the noise figure of NF1. Second amplifier has a AP2 gain and then noise figure 2. Third amplifier is has a gain of AP, ini sepatutnya 3 lah. Okay, and this is NF3. Kalau kita ada lebih banyak, maka dia akan ada AP of N and also noise figure of N. Okay, sehingga N. Dia tulis N ni sebab dia sehingga N lah sebenarnya. So kalau dilihat di sini, SO over NO is equal to SI over NI plus NF total. So ini jangan keliru. So isunya sekarang, okay, the issue now is we want to find F total and also NF total. This is the issue now. How to calculate this? We need to use the Friis equations yang atas ni. So total F for cascaded system is equal to F noise factor of the first amplifier. Okay, noise factor of the first amplifier. Dalam case ini kita perlu buat anti-lock lah untuk yang ini. Kalau kita compare dengan gambar ni, because this picture give the value of NF. So in order to find the F1, we need to do the anti-lock. Okay, remember that NF adalah bersamaan dengan 10 log F. So if we want to find F, we need to do anti-log of NF. Okay, so noise factor of first amplifier plus noise factor of second amplifier minus 1 divide with the gain from the first amplifier. Okay, so bermakna apabila tadi dia dah masuk ke dalam amplifier yang satu and then dia move kepada amplifier yang kedua. So what happened is that the way we calculate is that F2 minus F1 divide the gain from the first amplifier. Okay, and then the signal moves to the third amplifier. Okay, we look here. Kita lihat di sini. F3 minus 1 divide with the gain from the previous, which is A1 multiplied with A2. Okay, so kalau sistem ini cuma ada 3 amplifier, if the system only has 3 amplifiers, that means we stop until here. But if there's more than 3 amplifiers, sekiranya ada lebih daripada 3, then we need to calculate one by one. sehinggalah n amplifier, sehinggalah amplifier ke n. So the way we calculate is Fn minus 1 divide with total gain from the previous. So A1 multiplied with A2 multiplied with A3 multiplied with A4 until An minus 1, until the previous. Okay, so we get a value of f, which is a unitless parameter. Okay, be careful that all parameters inside the Friis equation must be a unitless parameter. Berhati-hati maknanya setiap parameter dalam Friis equation ini mestilah unitless. F unitless, of course, F adalah unitless. Gain must be unitless. You cannot put gain in term of decibel. Berhati-hati common mistakes by the student from the previous semesters, apa yang berlaku adalah dalam soalan diberikan gain dalam decibel. Dia terus masukkan dalam Friis equation. Maka jawapannya salah. Okay, the gain inside the Friis equation must be unitless. So A must be unitless, F also unitless. Kesilapan pelajar diberikan NF, dia terus masukkan nilai NF dalam equation. Itu salah. So the thing is that you need to remember that all parameters inside the Friis equation must be unitless. Semua sekali. Okay. Nanti kita akan lihat contoh ada. F total, total noise factor, and then noise factor for each of the amplifier is F1, F2 until Fn. The gain of the amplifier A1 until An. Notification remarks. Ini yang tadi saya cakap. Change unit of all noise factors F and power gains A from decibel to unitless before insert into the Friis equation. So berhati-hati. Okay. Example. Example 2.9, the input signal to teleconnection receiver. Okay, so needed. Okay. So dia ada tanya SNRI dan juga SNRO. So this is a receiver. The receiver says, okay. So I would strongly suggest to students, when you are given these kind of questions without picture, so why not you draw for yourself? Okay, lukislah untuk diri anda sendiri. Okay, something like this. Saya punya lukisan pun tak adalah cantik kalau dilihat. So you see that here the receiver consists of 100 microwatt of signal power. Okay, this is from the input. So the input SI is equal to 100 microwatt. And then the NI noise is equal to 1 microwatt. And then what? The receiver contributes an additional of 80 microwatt. So at receiver ini, dia ada parameter ND equal to 80 watt. Sorry, 80 microwatt. Microwatt. And it has a power gain AP equal to 20 dB. So what? So compute the input SNR, compute the output SNR, and the receiver noise figure. So ada 3 soalan yang ditanya. Okay, so we don't know how much is SNRI, SNRO, and we want to find NF. Okay, so SNRI, first question, SNRI is equal to SI over NI. So 100 micro divided with 1 microwatt. So we get 100. 100 in terms of decibel, 10 log 100, which is 20 decibel. Okay, so class, if you see from here, soalan tidak spesifik meminta dalam sebutan decibel. Okay, the question doesn't specifically mention about you need to find this parameter in terms of decibel or unitless. Okay, in that case, you can stop until here, 100 is enough. But why this example proceed until dB? Because in the real world, in the real practical world, dalam practical world biasanya kita nyatakan SNR dalam sebutan decibel. Kita biasanya tak nyatakan dalam unitless. Dalam dunia sebenar, practical world, apabila ditanya tentang SNR, berapa SNR? So biasa kita sebut dalam sebutan dB. Okay. So I move to the next question. The next question asks about SNRO. Nak cari SNRO, kita perlu cari SO over NO. Saya lebih prefer cari SO terlebih dahulu. Okay, sebab dia mudah. SO adalah bersamaan dengan gain multiplied with the input signal power. So the gain here is given as 20 dB. Tadi gain diberikan 20 dB, 20 dB of gain. So 20 dB kalau you anti-log dia akan jadi 100. Okay, anti-log 20 bagi 10 and then anti-log of 2 you get 100. Okay, so 100 multiplied with 100 micro of input signal power. So we get output signal power 1 times 10 power of 2, 10 power of minus 2 watt. Okay, kemudian baru kita cari N out. So N out is equal to internally generated noise, which is 80 micro given in the question, plus 100 gain multiplied with the input noise, 1 micro. So we get output noise equal to 1.8 multiplied with 10 power of minus 4. Cuba students, please try using your calculator to calculate these parameters. And then output SNR, now we want to calculate the output SNR equal to S out over N out. So we divide the output signal power over output noise power. So we get 55.56. And in terms of decibel, we get 10 log 55.56, we get 17.45 dB. Okay, straightforward kita convert kepada decibel. Noise figure. The third question, soalan ketiga dia tanya berapakah noise figure, NF. Noise figure is 10 log of F. That means we need to find F. Okay, kita perlu cari nilai F. So yang ini adalah F, which is SNRI over SNRO. Tadi SNRI adalah 100, which is ini, this one, 100. Divide with SNRO, which is 55.56. So you see that I'm not putting the decibel value. Jangan masukkan decibel value, berhati-hati. So we are using the unitless parameter. 100 divide with 55.56. Okay, remember, don't put the decibel value. Be careful. Okay. So we get 100 bagi ni kalau guna calculator 100 bagi 55.56, so 1.79985. So 10 log of answer, so you're gonna get 2.55 dB. So berhati-hati di bahagian sini, be careful. Okay, dia bukan menggunakan decibel, berhati-hati. And then this one, example 2.110. Okay, ini example ini, this example, we have give this example in the previous semester's test question, long time ago. Kita bagi sebiji sama tepat, exactly the same. Okay, bagi sama tepat. Long before the COVID, long before the pandemic, we give this question in the test. Surprisingly, many students are unable to answer correctly, and there's also many students can answer this example correctly, but surprisingly also many students unable to answer. Itu yang kita surprise sedikit, sebab dia dalam nota kita ambil sama, tak ada tukar apa pun. Okay, so that one is a long time ago, but now it's online, so you can open book, so no problem. Okay, so back to here, you see that input signal power, this is a SI, input noise power NI, power gain, this is AP, this is ND. So you are given this, find the three parameters, SNRI, SNRO, and also F and also NF. So find one by one. So SNRI is SI over NI, which is 2 times 10 power of minus 10 divided over 2 times 10 power of minus 9 minus 18 for the input noise. So you get 1 times 10 power of 8 for the input SNR. So in terms of decibel, so you see that the question specifically mentioned you need to find in decibel. So of course, it is mandatory to find the decibel. So 10 log of 1 times 10 power of 8. So you get 80 decibel. Kalau dalam decibel lagi senang nak tulis 80. Berbanding yang ini kena tulis darab. Okay, so 80 decibel. Output noise power. Okay, so I would suggest to find S out first because this is easy parameter to find. So gain multiplied with SI. So the gain is given as how much is the gain? Gain is 1 million. So gain is 1 million multiplied with input signal power. So we get 2 times 10 power of minus 4 watt. Okay. And then N out is equal to internally generated noise plus input noise multiplied with the gain. So this is internally generated noise 6 micro plus this is the gain multiplied with the input noise. So we get 8 times 10 power of minus 12 watt. Okay, daripada sini then we can calculate the SNRO. SNRO is equal to dalam sini dia terus cari So 10 log SO over NO. Okay, so we get 74 decibel. Okay, and then what? The next question asks, how much is the noise factor? Noise factor is SNRI over SNRO. Nah, ni So tadi SNRI adalah 1 darabkan dengan 10 kuasa 8 Okay, 1 darab 10 kuasa 8 dibahagikan dengan input yang tadi ini nih. 1 darabkan dengan 10 kuasa 8 for the input SNR, and then for the output SNR this is 250,000 So ini berapa ni? 2 juta 1 2 3 4 5 6. So 25 million. So this is actually 25 million. So kalau you bahagikan yang ini if you divide this one, you're gonna get 25 times 10 power of 6. Okay. So 25 million 1 2 1 2 3 4. Okay, 25 millions. So, kita tak nampak ni tadi sebab dia tulis 74 decibel tadi Dia tulis 74 decibel sebenarnya adalah bersamaan dengan 25 millions. So when you divide, you're gonna get 4. Berhati-hati di sini jangan tulis decibel be careful. So when you get 4, then you can do the log function. So in noise figure NF, 10 log of F. So 10 log of 4, you're gonna get 6.02 decibel. Okay, so baru di sini kita dapat sebutan decibel. Boleh setakat ini? Kalau ada soalan nak tanya, boleh tanya. Kalau tidak ada, saya akan proceed. Boleh So saya proceed. If it is clear, so I will proceed with the next question. So pelajar-pelajar, if you have questions to ask, you can stop me anytime. You can ask me questions, okay? So I will proceed with example 2.11. For a 3 cascaded amplifier stages each with noise figure of 3 dB and power gains of 10 dB. So kita ada 3 amplifier yang serupa, yang sama. Okay, because this is similar. So this is amplifier 1 connected to amplifier 2 connected to amplifier 3. Okay. Dan dikatakan di sini bahawa you are given noise figure NF, NF1 equal to 3 dB, NF2 also 3 dB, NF3 also 3 dB. And then what? Gain. So gain you are given AP1 equal to 10 dB, AP2 equal to 10 dB, AP3 equal to 10 dB. Okay, 10 dB. Okay, so what? So the question asks, determine the total noise figure. Dia nak cari nilai NF total. In order to find NF total, first of all, you need to find F total. So how to do it? We need to find F total using the Friis equations. Okay. So in order to use the Friis equation, we need to convert the decibel into a unitless parameter. Untuk menggunakan Friis equation, kita kena tukar. Tak boleh pakai decibel. So what happen is that we need to convert the value of gain. 10 dB, if you do the anti-log, you akan dapat 10. Cuba bagi 10 bagi 10 dapat 1, anti-log of 1 you gonna get 10. Okay, anti-log 1 dapat 10. And then what? Anti-log of NF. Anti-log of NF, you're gonna get F. Okay, anti-log of NF1, you're gonna get F1. Anti-log of NF2, you're gonna get F2. Anti-log of NF3, you're gonna get F3. So maknanya di sini F1 equal to F2 equal to F3. Anti-log of 3 dB. So 10 bahagi 3, 3 bagi 10 3 bagi 10 0.3, and then anti-log 0.3, you akan dapat 2. Okay, so now we have A parameter, we have F parameter, then we can put inside the equation. Okay, so F total is equal to F1, okay, plus F2 minus F2 minus 1 divided with previous gain from the first amplifier, and then plus F3 minus 1 divide with A1 multiplied with A2 from the this is from the previous amplifiers. Okay, so that means 2 plus 2 minus 1 over 10 plus 2 minus 1 over 10 times 10. So you get 2.11. So this is the F total. Belum selesai. Dia tanya NF total. Soalan tanya NF total. So NF total is 10 log of F total. So you get 3.24 decibel. Perhatikan So when you see from here, how can we make sure that the total noise figure will be as small as possible? Macam mana kita nak pastikan total noise factor ini sekecil yang mungkin? How to do that? So if you see from the equation, we must make sure that the first F must be as small as possible. Okay, maknanya apa? Saya perlu pastikan bahawa the first device, device yang ini, yang pertama ini, mestilah mempunyai noise factor yang paling rendah supaya total noise factor menjadi kecil. Dia bukan maknanya kita increase, it's not because we increase the gain, no. You see that if you increase the gain, you only reduce the second parameter and third parameter. Kalau kita tinggikan gain, kita cuma akan mengecilkan second and third parameters only. But if you make sure that the first device has the lowest noise factor, then you can make sure that the overall noise factor gonna be reduced. Itu sebabnya dalam susunan amplifier, sebaiknya amplifier yang mempunyai noise factor yang paling kecil mestilah berada di depan. Okay, amplifier yang menghasilkan noise factor yang paling kecil perlu diletakkan pada bahagian yang pertama, yang first kali. Disusuli oleh amplifier yang mempunyai noise factor yang kedua terendah dan ketiga terendah dan seterusnya. Kalau disusun seperti itu, maka kita akan dapat total noise factor yang rendah. Itu biasa keluar dalam soalan macam tu. So ini nanti saya akan tunjuk contoh yang tu. Okay, susunan itu berkenaan dengan susunan amplifier. Kita akan susun amplifier yang mempunyai noise factor yang paling rendah mesti di depan, followed by second lowest, third lowest noise factor. Okay, yang paling depan mesti noise factor yang paling kecil, kedua adalah yang kedua terkecil, ketiga terkecil dan seterusnya. Barulah kita boleh make sure yang dia punya total noise factor menjadi rendah. Okay. So I go to the next topic, which is equivalent noise temperature. So the equivalent noise temperature is so ini KTB. This is PN. PN is equal to KTB. So I want to show this one. Okay. Equivalent noise temperature is the noise temperature that exists inside the system. Okay, it is produced by the system itself. Okay, dia wujud di dalam sistem disebabkan suhu dalam komponen sistem itu. So it is denoted as a TE. So TE, the lower the TE, the better would be the quality of the receiver. So kita inginkan TE ini serendah yang mungkin. So TE ini bukan ambient. Ambient temperature adalah T. So TE ini di dalam device. Di dalam device. Okay. So the relationship between TE and F adalah TE equal to ambient temperature multiplied with F minus 1. TE is the equivalent noise. T is the environmental noise. Suhu bilik, suhu sekeliling. Okay. So kalau diberikan dalam ini bermaksud 17 degree lah dalam kes ini. So by default, okay, by default we assume that room temperature is 17 degree. Unless it is given a different value in the question. Okay, melainkan ada value yang berlainan dalam soalan. Okay, kalau diberikan 20 degree Celsius, you kena tukarlah dalam Kelvin berapa. Okay, kalau 20, so the formula is you need to plus with 273 in order to convert from Celsius to Kelvin. Okay, so from here we summarize the equations to become like this. Okay, kita ubah sesuai soalan, ubah sesuai formula itu. Kalau F, kalau you susun semula soalan equation ini, F equal to 1 plus TE over T. Okay, F equal to, okay, yang tadi ni dalam Kelvin, TE dalam Kelvin, TE dengan T dalam Kelvin. Okay, so this so now we know the relationship. Okay, example. So determine the noise figure for an equivalent noise temperature 75 Kelvin, and then equivalent noise temperature for a noise figure 6 dB. Okay, let's do the first one. Noise figure for an equivalent noise temperature of this one. So we want to find NF. Okay, in order to find NF, we need to find F in the first place. Okay. F is equal to 1 plus TE over T. Ini daripada equation yang tadi. F equal to TE, 1 plus TE over T. So here 1 plus 75, because the question gives TE equal to 75. Divide with 290. By default, the room temperature is 290 Kelvin or equivalent to 17 degrees Celsius. So we get 1.258. Okay. So tadi dia tak berikan berapa ambient temperature, tak diberikan. So dalam kes ini dia assume room temperature by default adalah 17 degrees Celsius, which is equivalent to 290 Kelvin. Okay. And then noise figure NF 10 log of 1.258. So we get 1 dB. Okay. And then what? The second question. You are given a noise figure 6 dB. So we need to find the equivalent noise temperature. So we need to find TE. Kita nak cari TE pula. So in order to find TE, so you are given NF. So anti-log of NF, you're going to get F, noise factor. Anti-log of 6 dB, so you akan dapat 4. Anti-log of 6. Okay, 6 divided with 10, which is 0.6, and then anti-log of 0.6, you're going to get 4. Okay, dapat 4. Equivalent noise temperature. TE is equal to T multiplied with F minus 1. Okay, so this is 290 divide with 4 minus 1, so it is 870 Kelvin. So tadi masukkan ni lah 4 kat sini. So F minus 1, so 870 Kelvin. Okay. Okay. Ini kalau tak ada soalan, saya akan terus topik yang terakhir, noise measurement. To work with a noise in the communication system, it must be measured in a meaningful way. So noise is a random process and does not have a single value or an equation to describe it. So the RMS, the root mean square value of the noise, is most important fact. RMS is formed by taking the square root of the average of the individual noise voltages which have been squared. So macam mana nak cari root mean square of the noise? How to find the root mean square of the noise? So consider this is example. In this example, we take the measurement of noise voltage. We have a 10 readings. Okay, kita ada 10 bacaan noise voltage menggunakan voltmeter. So dia measure menggunakan voltmeter sebanyak 10 kali. So dia dapat ada 10 value of noise voltage, which are minus 0.3 volt, 1 volt, 0.2 until here 0.9 volt. So how to find the RMS noise voltage of these values? Okay, so in order to find the RMS noise voltage of all the values, first we need to do the quadratic summation. Okay, do the quadratic summation, the first step. Okay, so the first reading square plus second reading square, third reading until the 10 reading. So the voltage squared. So we get 3.0325 volt square. Okay. The second step, okay, this is the first step. The second step, we need to find the average. So the average is the quadratic summations divide with the total number of reading. Dalam case ini dia ada 10 value, ada 10 bacaan. So that's why dia bahagikan dengan 10. Okay, bergantung kepada how many readings that you have. Okay, so we get the average, purata. Okay, purata setiap bacaan adalah 0.30325 volt square. Okay, and then what? The third step is the final step, which is, okay, third step adalah we do the root mean square of the average. Root mean square of the average, so we get 0.55 volt. So this is what we call as the root mean square of the noise voltage. Okay. Example. Noise value in millivolt as follows. So you are given 10 values of noise voltage in millivolt. Okay, dalam sebutan millivolt. So ada 10 bacaan yang diambil selepas kita measure sistem itu, didapati ada 10 value untuk pada masa-masa sekian. Okay, at different time we take the measurement, okay, and then we get the value. Okay, that means here ada 10 kali, maknanya ada 10 masa yang berlainan. Kita ambil bacaan, so the noise voltage at that time, at that particular time ada sekian. Okay, so find the RMS noise voltage for the readings. So here the first step, find the quadratic summation. So you get 24,751 millivolts square. And then find the average. Second step. 24,751 divide with 10 because we have 10 values. Cari purata. So we get 2075.1 millivolt square. So berhati-hati, the unit is square. The third step is find the RMS value. We do the square root of, is square root of 2475.1. Okay, so we get 49.75 millivolt. Itu dia. So itulah dia untuk mencari RMS noise voltage. So selesai. Okay. So that's all for chapter 2. I want to show you another example. I want to show another example which may be interesting to learn about this example. So you see, this is test 1. Bukan not this semester. Test 1, semester 1, 2014, 2014 and 2015. Long time ago. Okay, long time ago. Saya suka menggunakan example ini kerana dia in my opinion is a good example. So you see that let's look at the question number 2. Okay, explain the term of intermodulation distortion and with the aid of a suitable diagram. So in this case, you need to explain about intermodulation distortion. That means there's going to be 2 or more input. Okay, and then it produces a sum and difference frequencies, which is called as the cross product. And then you draw the graph, ada dua input dan ada sum and difference. That's it. Okay, simple. And then question number 2. Question number 2 is a bit tricky. It's interesting to learn about this. So you see that here we have a cascaded amplifiers. Okay, so you are given the ambient temperature is 17 degrees Celsius. Okay, ambient temperature 17 degree, which is 290 Kelvin. The signal transmission bandwidth is 300 megahertz. So B is 300 mega. And then what? The antenna. So you see that here, from here, the antenna given the input signal power 5 watt. You are not given input noise. Okay, tidak diberikan. And then amplifier 1, 4 dB, amplifier 2, 5 dB, amplifier 3, 20 dB. Equivalent noise temperature 77 degree Celsius for the first amplifier, 300 degree Kelvin second amplifier, 450 Kelvin for the third amplifier. You are not given the SO and NO, SNR output tidak diberikan. Determine the input signal to noise ratio in dB. Calculate the noise factor, total noise factor. Find the output signal power SO in watt and output noise power in dBW. Macam mana nak buat ni? So ini menarik untuk difikirkan. Sekejap. Okay. So how to do this? Kita boleh letak apa? Insert Jamboard. Open a Jamboard. New. Sekejap. Okay, tadi so kita lihat di sini ya. So tadi ada Jamboard yang ini. So mungkin kita buat sebelah-sebelah. Okay, so dalam kes ini NI so NI is equal to KTB. Okay, sebab dia tanya berapakah determine the input SNR. So input SNR, we need to find the SI and NI. We know the SI, we don't know the NI. Okay, so that means this is 1.38 times 10 power of minus 23 multiplied with temperature, which is 290 Kelvin, multiplied with 300 mega, 300 mega, 10 kuasa 6. Okay, so this one becomes 1.2 1.2 times 10 power of minus 12 watt. Okay, 1.2 picowatt. Okay, so SI over NI, so SI over NI is equal to SI is 5 watt divided with NI is 1.2 multiplied with 10 power of minus 12. Okay, which is equal to 4.167. Sorry, 4.167 times 10 power of 12. So this is ni dalam unitless parameters. So kalau you nak buat dalam decibel, so the question asks in dB, so that means you need to find in terms of decibel. So decibel 10 log of 4.167 times 10 power of 12. So we get here is equal to 126.198 dB. Ni boleh cuba. So 10 log 4 point. So this is 4 point. Sorry, 4 point. So 4.167 exponent 12. Okay, akan dapat 126.5. Dapat 5 aja 4.167 exponent 12. 10 log answer, so you're gonna get 126.198. Sorry, 126.198 dB. Okay, boleh cuba. Okay, that one is the first question. Okay, find the input SNR. And then what? Calculate the total noise factor, F total. So F total, kalau dilihat di sini, F total we need to find F for each of the amplifier. Kita perlu cari F untuk setiap amplifier. Okay, kita perlu cari F untuk setiap amplifier. That means we need to find F1 is equal to 1 plus TE1 over T, which is equal to 1 plus TE1 berapa? TE1 adalah 77 degree Celsius. 77 degree Celsius plus 77 plus 273. So kita akan dapat 350 Kelvin. Okay, 350 dibahagikan dengan room temperature 290. So we get this one is equal to 2.201. Okay, F2 is equal to 1 plus TE2 divide with T. So this is equal to 1 plus TE2 adalah 300 Kelvin. Okay, so ini macam mana nak besarkan dia. Okay. Okay. So TE2 is 300 Kelvin. So 300 divide with room temperature 290. So we get here 2.034. Ini boleh cuba guna calculator. Mana tahu saya tersilap. Tak perlu salin sebab ada video kan. So ni saya record. So you tak perlu salin. You kena fahamkan. Tak faham boleh tanya. Okay. So F3 is equal to 1 plus TE3 divide with T. So this is 1 plus 450. You are given 450 over 290. So this is, you're gonna get 2.552. So now we want to find the total F. So total F total is equal to F1 plus F2 minus 1 over A1 plus F3 minus 1 over A1 multiplied with A2. Okay. So dalam case ini kita lihat next page. That means dia akan jadi F total. F total. Dia akan jadi F1 2 point tadi F1 F1 2.201. Okay. 2.201 plus 2.034 minus 1 divide with 2.512. Ini A1. So 512. How I get this one? This is a anti-log of 4 dB. Anti-log of 4 dB, we get a anti-log of 0.4. Anti-log of 0.4, we get 2.512. Okay. And then what? Plus 2.552.552. This is F3 minus 1 divide with A1 multiplied with A2. A1 adalah 2.512 darabkan dengan A2. A2 is 5 dB. Anti-log of 5 dB we get 3.162. Boleh cuba anti-log 0.5 dapat 3.162. Anti-log kepada 5 dB tadi So 3.162 Okay. So you're gonna get the F total is equal to 2.201 tambahkan dengan 0.412 tambahkan dengan 0.195. Ini boleh bantu saya kalau saya silap 2.808. So dapatlah F total. Okay. And then what? Find SO and also NO. So you see that interestingly at that time student tanya berapa nilai NI? Macam mana nak cari SNRI kalau tidak diberikan NI? NI boleh dapat dengan cara mengira KTB yang tadi KTB you akan dapat NI. Okay. And then what? The third question asks about SO and also NO. Macam mana nak cari SO? So in order to find SO, first we need to find A total. Okay, kalau you lihat A total bersamaan dengan A1 multiplied with A2 multiplied with A3. So this is equal to anti-log of 4 dB. Okay, anti-log of 4 dB multiplied with anti-log of 10. So anti-log of 0.5 darabkan dengan darabkan dengan 20. Okay, the last one is 20, not dB. So you're gonna get 158. Ini boleh cuba kira 0.866 66. Okay. So from here, I can calculate SO in what? SO is equal to A total multiplied with SI. So A total is equal to berapa tadi? 5, diberikan 5 watt. Okay. So this is 158.866 multiplied with 5. So I'm gonna get the answer is equal to 794.328 watt. Okay, 0.328 watt. Dapat SO. And then what? NO. NO ni yang masalah sikit. So in order to find NO, first of all, I need to find how much is SNR. I can find how much is the SNRO. Okay, tadi kita dah dapat F tadi. We already have get the value of F. Okay, we already get the value of F. We already get the value of SNRI. SNRI dah tahu dah. Ini. So now maybe we can find SNRO first. Cari nilai SNRO. SNRO is equal to SNRI divide with F total. Kalau dilihat di sini, SNRI, okay, SNRI is equal to 4.167, 4.167. So 4.167 times 10 power of 12 divide with F total. F total tadi berapa? F total ni 2.808. So 2.808. Nah, ini berapa ni? So 4.167 eksponen 12 bahagikan dengan 2.808. Nah, ini tolong bantu saya. 1.484 kali 10 kuasa 12. Okay. So saya dapat SNRO. And then I already have SO. Saya dah dapat SO. Because this is actually equal to SO over NO. Okay. So in order to find NO, so I need to make it as SO. Sorry. Okay, SO. Okay, tadi kita dah dapat ni aja. Okay, saya dah dapat, saya nak cari NO, so this is SO over 1.484 times 10 power of 12. Tadi SO dah dapat. Yang ni. 794,328. Okay, so ni sini maknanya 794. So saya pergi ke sini lah, saya buat ke sini. Okay, so 794.328. So 328 bagikan dengan 1.484 times 10 power of 12. So dapat berapa? So 1.794.328. Ini tolong betulkan saya kalau salah. 1.484 eksponen 12. Dapat 5.3728. Betul ke? Kali 10. Okay. And then kalau kita buat anti-log, bagikan dengan 10, anti-log answer, 5.3328 eksponen negatif 10. Ini dapat NO. NO dia nak dalam dBW Okey, siap. 5.3728 eksponen negatif 10. Okey, so bahagikan dengan 10 dulu. Anti-log of answer. Saya dapat satu. Oh, silap. Sorry, 10 log. Okey. Sorry. 5.3728 eksponen negatif 10. 10 log answer. 10 log answer. Okey, dapat negatif 92. Okey, saya dapat bila kita jadikan dia decibel sekejap So NO so the question is NO in dBW is 10 log ni tadi 10 log of 5.3728 times 10 power of minus 10. Okay, so ni. So we get here, this is 10 this is 10. So we get minus 92.698 dB W. Dah baik, selesai. Okay. And then what? Ni pelajar-pelajar tak perlu salin dulu. Cuba fahamkan bantu saya guna calculator. Okay. Okay, the last one, the receiver output signal to noise ratio can be improved by using suitable configuration for the cascaded RF amplifiers. In your opinion, which RF amplifier should be placed at the first stage and why? So, kalau dilihat untuk susunan yang terbaik adalah kita perlu melihat F. Okay, that means you see that from these values, I can say that the second amplifier should be the first at the first stage. The first amplifier should be at the second stage. And the last amplifier should be at the third stage. Why? Because the noise factor is the least, is the minimum. We choose the second amplifier as the first stage because it has the lowest noise factor. That's the reason. So maknanya kita susun seperti ini amplifier number 2, amplifier number 1, and then amplifier number 3. Okay. Why we choose like this? So that because amplifier 2 has the least noise factor. Selesai. Ini pun berguna untuk you punya assignment berguna untuk you punya assignment that means you can also give a suggestion on to improve the arrangement of the amplifiers in order to get the minimum, okay, the least in order to get the best output SNR. Okay, so cara kita membuat susunan, kita berdasarkan nilai F yang paling rendah. Okay. Ini pun ada share. Saya sebenarnya baru first time guna guna Jamboard ni. So biasa kalau guna Microsoft Whiteboard tu jadi hang sikit. So ini tak ada hang, alhamdulillah, tapi nak dia punya feel menulis tu kurang sikit Feeling dia punya experience feeling tu kurang Berbanding whiteboard tu lebih menarik. Tapi tak apalah. So ini dia terus share kepada pelajar. So nanti you boleh lihat lah. Okay. So itu sahaja. Ini pada ketika dia tengok dah lah penat-penat buat cuma dapat 17 markah je. Kesian Okay, so yelah. after this test, we found out that we should give more marks for the question actually. Okay, so don't worry. So in your for your information, saya boleh kata ini antara soalan yang paling susah test masa dulu lah at that time. Okay, so if you can answer this question, I believe you can score this semester, no problem. So itu sahaja. Sorry to take a long time. So semua boleh buka ni ya. Your QR code scanner. So after you scan, you can go out and go to the next class. Okay. Okay, sambil scan tu bolehlah tanya soalan, apa-apa soalan yang nak tanya boleh tanya sambil kita scan kehadiran. Okay, so section 1. So today is ni. Okay. So QR code. Okay, boleh scan. Siapa dah scan boleh keluar, boleh pergi ke kelas lain.
Masih Doktor.
Okay, sama. See you again next week.
Terima kasih Doktor.
Okay, sama.
Terima kasih Doktor.
Sama.
Thank you, Doktor.
Terima kasih Doktor.
Okay, welcome. Okay, sama.
Thank you Doktor.
Thank you, Doktor.
Siapa lagi 5 orang ni? Pelajarnya dekat sini.
Terima kasih Doktor.
Okay, sama. So 5 orang ni boleh scan ke tak boleh?
Doktor, saya buka guna phone tu ada
Nama siapa? Nama siapa?
Nur Firdaus.
Nur Firdaus ni
Ya saya.
Okay, saya dah tick dah.
Terima kasih Doktor.
Syahira.
Siapa?
Nur Ain Syahira. Nur Ain Syahira.
Nur Ain Syahira. Okay.
Thank you, Doktor.
Okay, welcome.
Terima kasih, Doktor.
Okay, sama. Siapa lagi? Tak ada 1, 2, 3. Okay, so itu sahaja kelas pada hari ini. So stop sharing.
Doktor,
Ya,
Arif Izzuddin tu dia ada masalah internet untuk scan attendance.
siapa nama dia?
Muhammad Arif Izzuddin.
Sekejap Muhammad Arif Izzuddin. Arif Izzuddin bukan dah.
Dia dah lepas
Muhammad Arif Izzuddin dah. Dia dah ni dah.
Okey.
Dia
Okey,
dah
Doktor.
scan dah. Okay, sama.
Okay.
So 2 orang tak hadir lah. So okay, itu saja. So saya nak stop recording.